Hey there, in this video I want to talk about the relaxation method for partial differential equations. So what we're going to do here is very similar to what we did with ordinary differential equations. The only difference is that ordinary differential equations only has one independent variable, whereas partial differential equations have multiple. So we just do the finite difference rule a few times. This is perhaps best explained by way of example. So let's do Laplace's equation. And so this is used here to find, say, the voltage in empty space, in the case where there are no free charges. Okay, so if we write this out in two dimensions, we have the second partial derivative of v with respect to x plus the second partial derivative of v with respect to y is equal to 0. Okay, and so we're going to do our finite differences twice. We're going to do it for the x's and we're going to do it for the y's. So with the x's, we're going to get v at x plus h, leave y alone, plus v at x minus h, leave y alone, minus 2 times v at x and y. Divide all of that by h squared. And then for the y's, we're going to have v, leave x alone, take y plus h, plus v, leave x alone, take y minus h, subtract 2 times vxy. Divide all that by h squared, set it equal to 0. Now, if we simplify this, we can multiply both sides of our equation by h squared to get rid of that term. We are trying to solve here for v of xy, and there's a total of 1, 2, 3, 4 of those. So when we rearrange this, we're going to end up dividing by a factor of 4. And then we have these terms, which are basically, you could think of them as adjacent to location v. So it's like to the right of v, to the left of v, above v, below v. Or above the point xy, I should say. Okay, so then we're going to have those 4 surviving terms. X plus h and y, x minus h and y, x and y plus h, and then finally x and y minus h, so the 4 neighbors. And it's typical that once you've done this, you get these sort of neighbors showing up with some kind of weighting. Now, different equations will give you different final results. We can't do this just once. So you do a different equation, you have to go back up to this step and then do the finite differences. But you end up getting something that looks like this. So let's come up with some boundary conditions for this thing and try plotting it over in the notebook. So here we are back in the notebook, and I've copied down the last line of our transformation of Laplace's equation. And so in effect, what this is telling us is that v is equal to the average of its neighbors, where the neighbors are left, right, up, down in a 2-dimensional array sort of sense. Now, to make this a complete problem, we have to have boundary conditions. So this is just generically Laplace's equation, period. And with different boundary conditions, we get different solutions. So let's say we have a square region, and let's go with the voltage being plus 1 volts on the left of our square region. Let's make it negative 1 volts on the bottom, and then 0 on the other sides. Okay, so that should give us something that's interesting looking. So I want to start here with an initial guess that we're going to relax from. So if this is too wacky, it's going to take a long time to converge. It might not even work at all. Also has to include our boundary conditions. So zeros will work for 2 of our boundary conditions, but we're going to have to modify the array to have the other 2. And so let's go with 101 by 101. I like these odd numbers because it gives us a grid point in the very middle. Okay, so now to get the other 2 boundaries, I'm going to have to change some of the values in here. So left here would be basically taking the first column out of this 2-dimensional array. And we're going to set that equal to 1. And then the bottom would be taking the last row out of the array and setting that equal to, I -1. Okay, so this will be an array that's kind of mismatched at the moment. It's going to have 1s or -1s on 2 of the sides. Everything else is 0, and now it's going to have to relax from that inconsistent solution to give us the actual solution in hopefully a fairly small number of steps, depending on whatever tolerance we set. Okay, so the for loop here is, well, this for loop could be a while loop, like I said in an earlier video. I like for loops because they will eventually end no matter what. And so we'll say 1,000,000 is our limit here. We want to save an old value of the array. Remember, we want to use copies here for our 2D array. And then we want to turn this into Python code. Okay, so we're going to do b from 1 to -1 and 1 through -1. So this is the inner part of the array. It never touches the outside edges because those are our boundary conditions, and we're not allowed to change those. And then we're going to have our averaging here. So we'll multiply by 1/4, and we want v up, down, left, right. Okay, so our slicing here is going to resemble the one-dimensional case we did with ordinary differential equations. So we're going to have 2's as the star of our show. And so, let's say we go 2 to the end, and then we have to have our second set of indices here if we're going to do a 2D array. So we want to be careful. We don't want to ever touch the boundary conditions. So we're going to make those 1 through -1. Okay, and the pattern will continue here. So this will go up to -2, 1 through -1. And so that's us messing around with the rows and leaving the columns alone. And now we're going to do the reverse. So the rows will be left alone. And we're going to do columns, rows left alone, and columns. And then, so we want to take a check here. So if the max value of the absolute value of the difference, v minus v last, is less than our tolerance, let's say 1 part in 1,000,000, just to make up a nice tiny sort of number, then we are happy. So we print some kind of message. At least while we're testing, it's a good idea to do that. And so solution converged in I plus 1 steps. Get out of my for loop. And if we never leave our for loop, this else clause is going to trigger. And so we want to print some kind of warning about it. Solution failed to converge. It will make it exclamation point because it's dire. All right, and if we run this, oh, what do we do wrong? Float object is not callable. Oh, I forgot to multiply. Yes, and now we get the second error message. This one was actually intentional. The previous one was an oversight. This one I meant to have happen. Okay, what has happened is this line right here is not happy. So regular Python max is not good enough when we're doing 2-dimensional arrays. It's okay with 1-dimensional arrays, like it understands what to do there, but with 2D arrays, basically it does this comparison on just one axis. So it's trying to compare entire rows with each other. It can't do it. The solution here is not so bad. We just need to use NumPy's version of max. Which does what you would expect and finds the overall max value in no matter how big the array is, instead of finding just like the biggest row, which is what Python's max does. Okay, so this converged. It only took about 5,000 steps, and now we want to show it. Now, when we do an imshow here of a 2D array, remember we have the choice of whether to set origin equals lower or not. It kind of depends on how we set up our data in the first place. And if I think about what I actually did here, I did the 2-dimensional array as if I don't want to flip it with origin equals lower. So for example, the bottom here, I made the bottom of the array equal to -1. I didn't make the smallest y coordinates equal to -1. So to be consistent with what I set for my boundary conditions and what I said I meant to do, I don't want to do origin equals lower. Whether or not you make that choice depends on how you set things up as far as drawing your array or creating your array up here versus drawing your array down here. All right, so I think it'd be a good idea to show a color bar. I like seismic in this case because it's very vivid. You've got the reds, the blues, and a white right in between. So I'm looking for, it's very patriotic. I'm looking for a red left at +1, a blue bottom at -1, and a white top and right. So let's see if that's what I actually see. Yep. So here we have this lovely, very patriotic graph of +1, -1, 0 here, and it shouldn't be too surprising that there's this diagonal line of zeros separating the left from the right. All right, so here we saw an example of applying the relaxation method with partial differential equations. Depending on the equation, you do have to rewrite what the finite difference rule actually gives you, but once you have that, it's effectively some kind of weighted averaging of neighbors, and just like for ordinary differential equations, we run it through a for loop, we check against a tolerance. Do be careful about, if this is a multidimensional array, which max function you're using. But other than that, same kind of idea, and we get our result at the end.